In electrostatics, the foundational rule is Coulomb's law. It states that the electric field generated by a point charge weakens proportionally to the square of the distance from that charge. This chart shows the decay. As field lines radiate in 3 dimensions, they spread, diluting the field's strength. But if we stretch that point charge into an infinite 2-dimensional sheet, the decay curve vanishes, replaced by a perfectly horizontal line. This implies the field of an infinite sheet never weakens. Whether 1 millimeter or a light year away, you experience the exact same force. But if we wrap that plane into a hollow spherical shell, the internal field instantly drops to exactly 0. Inside this sphere, you are completely surrounded by electric charge on all sides, yet you experience absolutely 0 electric force. To prove these mathematical realities without relying on impossible vector calculus integration, we will use Gauss's law and the concept of spatial symmetry. We begin by defining the continuous variable for our infinite plane, the uniform surface charge density, denoted by the Greek letter sigma. Trying to calculate the field by summing up individual point charges across an infinite space using standard calculus is a massive mathematical headache. We need a geometric shortcut. Looking at this 3D view of an infinite charged plane, we can establish its spatial symmetry. Because the sheet stretches infinitely in all directions, the resulting electric field cannot have a vertical y or depth z component. It points strictly outward along the x-axis. For every specific charge pushing a test particle up, there is an identical charge on the opposite side pushing it down. All these angled forces cancel each other out, leaving only the vectors that are perfectly perpendicular to the surface. This specific symmetry dictates our ideal Gaussian surface. We construct a rectangular parallelepiped, a pillbox, that pierces directly through the sheet. The utility of Gauss's law depends on selecting a surface where the electric field is either perfectly parallel or perfectly perpendicular to every face. Now we calculate the total electric flux through this Gaussian pillbox using the standard equation. Total flux equals the closed integral of the electric field E dotted with the area element ds. First, we examine the 4 side faces of the pillbox. Here, the normal area vectors point outward, making them perfectly perpendicular to the electric field. Because the dot product of perpendicular vectors is mathematically 0, these 4 sides experience no flux. The field simply runs parallel to them, never crossing the boundary. That leaves the 2 end faces. The electric field punches straight through these surfaces, sitting perfectly parallel to their normal vectors, at an angle of 0 degrees. The flux here is maximized. We take the cross-sectional area A of each end face and multiply it by the field E. With 2 faces, our total flux is 2EA. Next, we determine the amount of charge enclosed by the pillbox itself. It is exactly the surface charge density, sigma, multiplied by that same cross-sectional area, A. Gauss's law sets the total flux equal to the enclosed charge divided by the constant epsilon naught. So we write 2EA equals sigma A over epsilon naught. Because the area variable A appears on both sides, it cancels out completely, leaving us with the final equation, E equals sigma over 2 epsilon naught. Notice what is missing from this equation. The distance variable r has entirely vanished from the math. This proves that the field strength remains constant, regardless of how far away from the sheet you travel. Now we apply this exact same geometric logic to our second paradox. A thin, 3-dimensional spherical shell with a radius of capital R and a uniform surface charge density. The total charge on this shell, Q, is the surface charge density multiplied by the sphere's total area, giving us Q equals 4 pi r squared sigma. To find the field at any point outside the shell where lowercase r is greater than r, we construct a larger, concentric transparent sphere. By spherical symmetry, the electric field E is constant and perfectly parallel to the normal vectors ds everywhere on this outer surface. This simplifies our flux calculation to just E multiplied by the surface area of the Gaussian sphere, 4 pi r squared. We set this flux equal to the total enclosed charge, Q, divided by epsilon naught. Rearranging the terms gives us E equals Q over 4 pi epsilon naught r squared. From the outside, the hollow shell perfectly mimics a single point charge concentrated entirely at its center. The mathematics takes a sharp turn when we investigate the interior of the hollow shell, where lowercase r is less than capital R. We construct a new Gaussian sphere, this time located entirely inside the charged boundary. The left side of our flux equation remains the same, E times the surface area of this new, smaller inner sphere, 4 pi r squared. However, we must look at the enclosed charge. All the physical charge resides on the outer shell. Inside our new Gaussian surface, the enclosed charge is absolutely zero. This creates a mathematical inevitability. If the enclosed charge is zero, the electric field E multiplying the area must also be exactly zero, everywhere inside the shell. This internal null field results from the exact inverse square nature of the force. The 1 over r squared decay ensures that vectors from all sides balance perfectly. If the universe operated on a decay rate of 1 over r to the power of 2.01, the opposing vectors from the near and far sides of the shell would not perfectly cancel, and an internal field would exist. Because physicists can verify the complete absence of an internal field in a hollow conductor, this paradox serves as the definitive experimental proof for the precise inverse square law. These side-by-side charts show the stark contrast in how these two geometries relate to distance. The infinite plane yields a constant horizontal line, while the hollow shell yields zero inside, spiking at the surface before decaying outward. Competitive physics exams frequently test these specific graph shapes. Recognizing the flat line versus the spiked decay curve demonstrates an understanding of the concepts rather than just a memorization of the formulas. But there is a critical real-world caveat to the first chart. True infinite sheets do not actually exist. The constant field equation is merely a valid approximation for a finite sheet of charge, and it only holds true provided you are measuring near the middle and far away from the boundaries. As you approach the edges, the field lines begin to bow outward and curve. This phenomenon, known as edge effects, breaks the perfect perpendicular symmetry required for our Gaussian pillbox to work. Ultimately, Gauss's law is a tool of geometric exploitation. By recognizing the intrinsic symmetries of the physical universe, we can bypass impossible calculus integrations and distill complex forces down to elegant foundational algebra.